Okay, hello. I'm going to be doing this practice test. I'm going to be doing it fairly quickly. One of the reasons may be that I just did a whole recording of this and no sound was recorded. So I wasted 30 minutes of my life there. But it's okay. But that does mean I might go through this a little more quickly since I'm losing patience. All right. First question, evaluating 5 simple logarithms. Well, first one, 32 is 2 to the 5th. So this is going to be 5. Second one, log base 8 of 2. Well, 2 is simply the cube root of 8. So we could write 8 to the 1/3 is equal to 2, which means that our logarithm evaluates to 1/3. Second one, there's no base, so that means it's base 10. Log base 10 of 100 is 2 because 100 is 10 squared. Log base 4 of 1 is 0 because 4 to the 0 is equal to 1. And of course, the log with respect to any base of 1 is always going to be 0. So this is 0. Log base 3 of 3 is 1. 3 is 3 to the 1. So, okay, second question. The idea is that we want to get everything under an exponent of base 2. So 1/2 is 2 to the negative 1, which means that the left side simplifies to 2 to the negative x, and the right side is 2 to the 8, if we remember our powers of 2, which we should. And this simply simplifies to x equals negative 8 by our 1-to-1 property. Third question, 2 simple logarithms to evaluate. The square root of b is simply b to the 1/2 power, so this is log base b of b to the 1/2, and this is equal to 1/2 by our inverse property. Second one, this is just negative 4, again by the inverse property. Okay, simplify the expressions. This is 4 based on, again, the inverse property. And the second one is kind of the second inverse property that we learned about, right? First one is log base a of a to the x is x. The second one is a to the log base a of x is also equal to x, right? So this is a second application of the second one, so this is 13. Second question, we can apply the 1-to-1 property, which means that the exponents are equal. This simplifies to x squared minus 15 equals 2x. We can rewrite it as a quadratic equal to 0. And if we factor this, that's x minus 5 times x plus 3, which means that x equals negative 3, comma, positive 5. And both solutions work because when we plug it back in, there are no issues. The exponential function has a domain of all real numbers. All right, second question has log base 2 of the 4th root of 8, and we can rewrite the 4th root of 8 as a power of 2, right? Because this is just log base 2 of the 4th root of 2 cubed, which is equal to log base 2 of 2 to the 3/4, which is equal to 3/4. Second question, ln of 1 over square root of e. Well, this is just ln of square root of e to the negative 1 power, right? Because reciprocals are just powers of negative 1, and the square root of e is just e to the 1/2 power. So this is ln of e to the negative 1/2, which is equal to negative 1/2. Okay, solve for x. 3 to the power of x is equal to 243. Well, if we remember our powers of 3, this is just 3 to the 5th. 81 times 3, right? So x equals 5. Okay, next one. 1/2 to the power of x is equal to 8. We can write both sides as powers of 2. The left side is 2 to the negative 1 to the power of x, which is the 2 to the x. 2 to the negative x, and the right side is 2 cubed. So x equals negative 3. Okay, here's our first graphing question. Given the parent function f of x equals 2 to the x, write the equation for the graph shown. Okay, there are 3 important things that we want to pay attention to when we see this graph, and these will help us to identify the equation. The first is that a horizontal reflection has been performed, right? Normally, the graph would look like this. It would increase as x increases, but now the graph decreases as x increases, which means that we have had a horizontal reflection performed. Second thing to notice is that the horizontal asymptote has not changed from the parent function, right? The original parent function asymptote would be y equals 0, and it still hasn't changed. What this tells us is that no vertical shift has been performed, okay? Because if a vertical shift had been performed, then the horizontal asymptote would have shifted up or shifted down, but we know that hasn't happened. It's possible that a vertical stretch was performed, but no horizontal shift, right? Because a stretch would not change y equals 0, but a shift would. Third thing to notice, y-intercept is no longer 0, 1, but it's now 0, 2. Okay? Normally for our parent function, right, 2 to the x, our graph would look like this. And the y-intercept would be at 0, 1. But now it's at 0, 2. And if there has been no vertical shift, then that indicates we have had a vertical stretch. Okay, so we can conclude that we have had two transformations performed. The first was a horizontal reflection, right? That's basically putting a negative sign in front of the x. And secondly, we know that a vertical stretch has been performed by a factor of 2, right? Because that would bring our 0, 1 to 0, 2. And we know that no shift has occurred. No shift up or down has occurred because the horizontal asymptote has not changed in any way. Okay, and so combining these two transformations, we are left with y equals 2 times 2 to the negative x, okay? The negative sign comes because we have had a horizontal reflection done, and the coefficient of 2 that comes to the front occurs due to this vertical stretch. And we can indeed confirm that this function has the same properties as we see in the graph, right? You can confirm plugging in x equals 0 that the y-intercept is 0, 2. And you can also see that this would have the same horizontal asymptote if y equals 0. And so you could write this as the answer, or you could also simplify it a little bit as y equals 2 to the 1 minus x power. Both are fine. Next question. Very similar, right? But in reverse. Find the horizontal asymptote and y-intercept of the following function and then sketch its graph. Okay, let's start with the horizontal asymptote. Well, first we should maybe notice that several transformations have happened, right? First, there has been a horizontal reflection because of this minus sign in front of the x. There's also been a horizontal shrink by a factor of 2 because of the 2 that's in front of the x. Then there has been a vertical stretch by a factor of 3 because of the 3 in front of the e to the negative 2x. And finally, there has been a vertical shift down 2 units because of the minus 2 outside the function, outside the parent function. All right, so originally, for the parent function e to the x power, the horizontal asymptote would have been y equals 0, okay? The horizontal transformations don't change the horizontal asymptote, but the vertical stretch by a factor of 3 also doesn't change it, right? Because the horizontal asymptote is originally just y equals 0, but a vertical stretch actually doesn't change anything here because this is simply the x-axis. However, a vertical shift down 2 definitely does change it, right? That sends our original y equals 0 horizontal asymptote to y equals negative 2. That would be our horizontal asymptote. Okay, you can also think about this algebraically. As x tends towards infinity, this is going to become a very small number close to 0, right? And so you're really only going to be left with this minus 2 as your y value as we go to large values of x near infinity. All right, let's do the y-intercept. Y-intercept is wherever the graph hits the y-axis, so that's where x equals 0. So we just plug in 0 into our function, and we're left with 3 times e to the power of negative 2 times 0 minus 2. The exponent simplifies to 1, or this is 0, which means that e to the 0 is 1. So we're left with 3 times 1 minus 2 equals 1. So my y-intercept is 0, 1. Okay? And the third important thing to remember before I graph is that a horizontal reflection has been performed. So I know that instead of increasing as it goes to the right, it should be decreasing, kind of like a decay function, right? So if I graph this, I'm left with this. I can start by drawing my horizontal asymptote. That's usually a good first step. Let's say this is -2. And then my y-intercept, right? 0, 1. That'll be around here. And I know that it has to decrease as it goes to the right. And so I'm left with a graph that looks like this. Okay? I want to make sure it comes very close to my horizontal asymptote. Next question, find the domain, x-intercept, and vertical asymptote of the following function. Let's start with the domain. Well, domain of the logarithmic function is pretty easy to find because we know that logarithms are only defined if the input is positive, okay? So that means to find the domain, we simply set the input to be greater than 0. 1 minus x greater than 0, and we can add x to both sides. That leaves us with 1 is greater than x, or x is less than 1. Okay, we could just write this, or we could write it in interval notation, which would be -∞, 1, open parentheses, right? Because 1 is not included. X-intercept, that's wherever our graph hits the x-axis, which is where y equals 0. So we simply find which values of x make our function equal to 0. And that means log base 3 of 1 minus x equals 0. And a logarithm only equals 0 when the input equals 1, right? You could see this clearly if you exponentiate both sides as powers of 3, right? On the left side, you would be left with 1 minus x, and on the right side, you would be left with 1. Either way, we're left with 1 minus x equals 1, or x equals 0. And so my x-intercept is 0, 0. Finally, the vertical asymptote is wherever my input equals 0. 1 minus x equals 0. You can think about this by thinking about how, for the input of a logarithmic function, it can always be positive, but it can never equal 0. Okay, so it'll always approach the line x equals 0, but never reach it for my normal logarithmic function. Okay, so that means I can just set my input equal to 0 to find the vertical asymptote, which means I'm left with x equals 1. To graph this, one very important thing to note is that not only do I have all the information here, but I also have a horizontal reflection, right? So normally my log function opens to the right, but now it's going to open to the left. So I want to pay attention to that. First, I'm going to draw my vertical asymptote. Now x equals 1. Draw that here. Let's say that's 1. And then my x-intercept is just the origin, right? So that makes it pretty easy to graph. It's going to start next to the asymptote and increase that way. Okay, I'm going to want to make sure that my graph actually comes very close to touching the vertical asymptote, right? A lot of people, when they graph it, they don't really make it come close. They make it look like that. That's not very correct. It's practically wrong, right? It needs to come very close to the asymptote. Next question. Here we're just going to know that whenever we subtract logarithms, their inputs divide, right? So this is log base 3 of 18 over 2, right? Make sure it's in the right order. The subtraction is in the same order as the division. So this is log base 3 of 9, or log base 3 of 3 squared, which is 2. Okay, remember 9 is 3 squared, not 3 cubed. Second one, we're going to do a change of base, and we apply our formula, and we're going to change to base 2. And the reason is because 8 and 16 are both powers of 2, so that's going to make it really easy to calculate. So log base 2 of 16 over log base 2 of 8. Okay, remember to put the 16 on the top and the 8 on the bottom. The base always goes to the bottom. Easy way to remember that, right, is simply by seeing how the 16 is already slightly higher than the 8 positionally. So it's going to go to the top. And this is going to be equal to 4 over 3 because log base 2 of 16 is 4, 16 is 2 to the 4th, and 8 is 2 cubed. Next question. Condense the expression to a logarithm of a single quantity. Here we're going to use our helpful formula. Whenever we have a coefficient in front of a logarithm, this is going to be as if we had an exponent on our input, right? So we can always bring a coefficient to the exponent of an input, and vice versa. An exponent can come out as a coefficient. So here we're going to be left with log base 9 of x to the 4th plus log base 9 of y to the 8th. And when we add logarithms, their inputs multiply, which means that this is log base 9 of x to the 4th times y to the 8th. And don't forget your parentheses. Next question. This is pretty straightforward. I just want to isolate each of the x, and so I'm going to do that, subtract 4 from both sides, divide both sides by -9, and I'm left with each of the x equals 1. Either just immediately see that x equals 0, or take a natural log of both sides, right? Natural log is log base e. So I'm left with x equals ln of 1, or x equals 0. Next question. Okay, this is a quadratic in terms of e to the x, right? And the reason for that is because e to the 2x is equal to e to the x squared, right? So this is just a quadratic equation. You could either factor directly, or you could write a substitution to make it more visually simple. So we can substitute y equals e to the x, right? And so we know that y squared is going to be e to the 2x. So this simplifies as y squared minus 2y minus 15 equals 0. Coincidentally, same factorization as before. Y minus 5 times y plus 3 equals 0. So y equals -3 or +5. Okay? Well, this -3 solution isn't going to work, right? Because if I plug my substitution back in, e to the x, e to the x equals -3 is invalid, right? Doesn't make sense. Exponentials can never be negative numbers. So that doesn't work. On the other hand, e to the x equals 5, of course, does work. In this case, I can take a natural log of both sides, and I'm left with x equals ln 5. That's my answer. Next question. I'm going to want to try to use the one-to-one property here because I have logarithms on both sides of the equation. But first, I'm going to have to simplify the left side into the logarithm of or into a single logarithm. Okay, so I'm going to use my addition property. This is going to be log base 4 of x times x plus 3 equals log base 4 of x plus 24. Here I can use my one-to-one property. I'm left with x times x plus 3 equals x plus 24, which means that x squared plus 3x equals x plus 24. I can simplify this into a quadratic. X squared plus 2x minus 24 equals 0, which factors as x plus 6 times x minus 4 equals 0, which means that x equals -6 or +4. Okay, so I have two solutions, but one certainly doesn't work, right? Because for any logarithmic equation, I definitely want to plug my solutions back in because logarithms have a restricted domain. They can't have negative numbers or 0. They can only have positive inputs. And negative x, right, that causes both of these logarithms to have negative inputs, so that's not going to work. So I'm only going to be left with x equals 4. Okay, last question before last page is a word problem. I'm not going to read it, but I'm going to use my exponential growth, right? Exponential growth function, r of t equals my initial value times my exponential factor to the power of little t over big T, my period of growth. Okay, what's my initial value? It's 10. It's doubling every 3 hours, so I know my factor is 2. And then little t stays as my variable, and big T, my period of growth, is 3 hours. It's doubling every 3 hours, so that's my period. And, oh, forgot to write 3 here. But otherwise, that's my answer for the function. And then the second part of the question, how many hours must elapse for the number of rabbits to exceed 1,000? Okay, so I'm essentially looking for the value of t such that 10 times 2 to the power of little t over 3 is equal to 1,000. So I can isolate the exponent to one side. I'm left with that, which means that t over 3, okay, all I'm doing is taking a logarithm base 2 of both sides. Log base 2 of 100, which means that t equals 3 times log base 2 of 100. Okay? And that would be my answer. Hours. If this was a science class, you would definitely need the units, but since it's math, we can let it slide. And then the final question, the final page, you can simply look at the solutions, and those are all the things you need to show in order to receive full credit. This concludes this video, and I hope it was helpful.